So hello everyone, this is lecture 12 for solid state physics, and in the last lecture we completed the superconductors, and from today's onwards we're going to start the DOS, that is density of states. Okay, so if you haven't seen the previous lectures, then go first see them, then you're going to understand or have a better understanding of these topics. So let's start. What is density of states? So density of states in 1D, 2D and 3D for the following particles. Means what we're gonna study in this density of state? We're gonna study the density of state for one dimension, two dimension, three dimension, and for these particles. What particles? So first is non-relativistic free electron and relativistic free electron. So basically you need to understand what is the difference between the non-relativistic and the relativistic free electron. So generally people say that if speed is approaching towards c, then we will call it relativistic, and if it is not nearby c, then it is non-relativistic. That's how you people say that. But if you want to define a particular boundary or something, then you will say that if kinetic energy is less than of the particle, then its rest mass energy, then it will be non-relativistic. And if kinetic energy is greater than its rest mass energy, then it will be relativistic free electron. Okay, so here is the sub boundary. So we can see that for free electron, we know its mass 9.1 into 10 to the minus 31 kg, and C we know that. From that we find that for the electron, the rest mass energy is 0.51 mega electron volt. Now if the kinetic energy of electron is greater than this, then we call the particle as relativistic or the electron relativistic. And if it is less than this, then we'll call the electron as non-relativistic. After that, we're going to study about the density of states for photons. What are photons? We know that these are quanta of EM radiation, and its energy is given by E equal to h nu. And if there are n photons, then energy can be given by n h nu. Okay. Next, we will study about the phonons. Phonons are nothing but the quanta of lattice vibrations. In the solids, we find that all the particles gonna vibrate, and that vibration inside a solid gonna produce the waves, and that quanta of that lattice vibration is called phonons. So for a phonon, energy can be given by h cut omega, and if there are n phonons, then that will be multiplied with n. The energy of one phonon is h cut omega. Then we will study the density of states for magnons. What are magnons actually? These are the quanta of spin wave. In a atom or in any metal, we find that every atom work as a act like a bar magnet. So if you see that these are the spins and these are atoms, and they are acting like a magnet. So if we deflect this somehow this way, then it will repel this end, and then this, so it will just oscillate, and this oscillation will produce energy which by which these all gonna oscillate relative to each other. And this vibration due to spin, this wave produced from these spin vibrations, will be called the magnon. Okay, just like in the solid, that vibration of lattice is called the phonon. That's how the spin wave oscillations are called magnon. Okay, so the density of states of these particles we're going to study now. First, let's understand what we are meaning with this density of states. What is density of states? We will start from very basic, so don't worry about that. So in one dimension, it is defined as number of states per unit energy range per unit length. So what is density of states? It is defined as number of states per unit energy range per unit length. In one dimension, per unit length per unit energy पे कितने states हैं? The number of states will be defined as density of states. Means, let's say this is our energy, okay, and these are the high energy terms, these are low energy terms for a metal, okay, and this is E, and this difference will give us E plus DE. Now we need to find the difference, number of states between these energies. So the number of states given by this between these energies is called the density of states. Not density of states. That will call the total number of states between these energy. And when we divide it with this energy, means number of states per unit energy, will give us the density of a state. If we define a term GEDE, it's just a function. We defined it as these are the number of states in the energy range E and E plus DE. This unit or this quantity is called the number of states in the energy range E plus DE. Now the density of states rho E will be this number of states per unit energy. So total energy will be difference is dE, so divided by dE. So this will give us the density of states, number of states per unit energy. Or in the 1D case, we can also write it as per unit length, means the number of states per unit energy per unit length. So this also can be written in the form of this density of states. In 2 dimension, we will find that density of states is the number of states per unit energy range per unit area. For the 3D, it will be per unit volume and per unit energy. Okay, these are the same. So for a better understanding what we mean actually about these quantum states or density of states, or what are the energy states, so let's go back to some mechanics. There are two walls and a rope is tied both ends. Okay, so the number of modes of vibrations we count here means everywhere, whether in quantum mechanics we called them quantum states, those are nothing but just the modes of vibrations of the quantum particle. So in the normal state we're gonna study this from this rope. Let's see, this rope is here, so it can oscillate like this, upside and downside. This is the first mode, we call the fundamental mode. And it also can oscillate like this is called the second mode. It can also oscillate like this is third mode. And this also can oscillate like this is fourth mode. And nth, it can vibrate like this. Okay, so these, just like this, we have the energy states, means the higher energy states increased in the here. So these vibrations are nothing and these states are nothing, just a mode of vibrations. The higher mode of vibration will give you the higher energy terms and the lower modes will give the low. So for any particle of these, we just see that how they're gonna vibrate or how they will have the energy state. So here are some terms. For the rope, we know that lambda for this is 2L. If this length is 0 to L, then what will the wavelength for this first mode? That will be 2L. How? Because if this wave is completed like this, then we know that the crust to crust will give you the wavelength, and that will be nothing but twice of this length, 2L, this and this. So this to this length will give you the wavelength, that is 2L. And when you came to the second mode, here you can see this is wavelength, this is wavelength. When it come up, this will be the wavelength, that it will equal to this and equal to L. In next, we'll find that this is the wavelength and wavelength is decreasing. So we know this formula that lambda equal to L, lambda equal to L by 2. So it is, the general formula is lambda equal to 2L by n for the nth mode. Okay, when n tends to infinity, the lambda will be tends to 0, very small. And with lambda we can also find the frequency. We know that the speed of any wave is nothing but lambda divided by t, or lambda nu. Lambda f can write frequency. So lambda f, and f will be v by lambda. So f will be v by lambda and lambda equal to 2L. For this first mode, so v by 2L. For this, v by 2L by 2. For this, v by 2L by 3. For this, v by 2L by 4. So that's how we can get the frequency for every wavelength. For the nth, we have nv by 2L. So here we are seeing that with each mode, this frequency is increasing. And if frequency is increasing of the wave, then we know that energy of the wave is directly proportional to the frequency. Then energy also increases. Okay, so these vibration modes are nothing but energy states. So now how we gonna relate them with the energy state, and how we gonna find these number of states and the density for different particles? That's we gonna study. So just to this is for your understanding that what are density of states and what are energy states and how they are related to the vibration. So this example totally related to that. Okay, just like this we have vibrations of particles. Like in a we have already studied, or we will study particle in a box. And if there is this particle in a box, then it can have the energy states, the ground state, and that energy states depend on the vibration, the mode of vibration of that particle. So if the higher mode there, then it will be at the higher energy state, and if it has the low mode of vibration, it will be at lower state. So now to find the number of states, we need to understand this. Let's say this is a unit length of 100 centimeter. Okay, and we played some beads in the range x, it is 0 to 100. We placed some beads. Okay, and the distance between each bead is 2 centimeter. Okay, so number of beads in the range 0 to 100 will be 0 to 100 will be, if we call it x, it is x plus dx. Then this minus this divided by the distance between each will give you the total number of beads. So that will be from here it will be 50. Okay, so just this is for the understanding that how the number of beads are nothing but the as there were states in there. We are just having a analogy. So gx dx will be x plus dx minus x divided by that distance 2, and that will give us the number of beads. And that just how we are getting the number of beads, we will get the number of states. And for the density of beads, if we need to find the density of beads, then total number of beads divide by total distance per unit length, that will give us density of beads. And here let's just like density of beads, we want to have density of states. So from this graph we can see that we get the frequency, we get the lambda. Now we also can get the wave number k equal to 2 pi by lambda. Now for lambda equal to 2l, we will have k equal to pi by l. For lambda equal to 2l by l, we will have 2 pi by l. For lambda equal to 2l by 3, we have k equal to 3 pi by l. So we can see that for each mode we have a single value of k. For each mode we have single value of k, and it is increasing 1 2 3 4 5 6 7 8. So we can directly relate these states with k. So number of k's, if we find the number of k, we can find the number of states. Okay, so that's how we're going to relate this. To understand this, you have to see this lecture again and again for 2 3 times, then you will understand this very well. So we are just having this, like this pi by l, 2 pi l, 3 pi by l, 4 pi l, these are nothing but k values for the higher terms. Here energy is increasing in this way, k is increasing and energy is increasing. So the k number of k's will give me the density of number of energy states or anything. Just we need to relate k with them, and we can get the that number density or the density of states. So if from this scale, as we have the beads, now we have the k. So gk dk are nothing but number of k states in the interval k and k plus dk. Okay, so gk dk will give me the number of k states. Okay, that's well. Now if I need to find, just like I multiplied 100 minus 0 and divide by the each distance, that will give me the number of beads. That's how k plus dk minus k, that is dk, divide by the distance between each, that is pi by l. So divide by that dk, pi by l आ गया up ऊपर. So number of k will be dk l by pi. So I got the number. Now see, we solved the problem all. We get the number of k's, and for the density we need to define just this divide by this length. So number of k per unit length, that will be divided by dk again. So gk dk divided by dk will give me the density of states in the one dimension. Hope it is understood. If still it is not understandable, then you can comment your doubt. I will try to resolve that. Now you will understand it more properly. We take some examples. Just there is this question: find the density of states of non-relativistic free electron in one dimension and plot rho e versus e. This is nothing but energy and the density of states. So we calculate for k, but here in the question it is asking us for the rho e, density of states in terms of e. So we don't need to worry. We just need to find a relation between E and K. Then we can transform. Just from the question we are seeing that it is for the free electron. So for a free electron, we know that potential energy is 0. So we only need the kinetic energy, that is P square by 2m, and P is nothing but h cut k. So we can relate now energy with k. So P is h cut k, h square k square by 2m. Now we have E in terms of k. This relation is called dispersion relation. Okay, and any relation between E and K, omega and K, V and K, those all relations are called dispersion relation. So now for the density of states, what we need to find from this formula, we need to find dk in terms of dE. So we can interchange this, then we will get rho e. If we have here dE, then we will get rho e. So just we will differentiate this with respect to k, dE by dk, that will give us we know this formula gk dk equal L by dk. From the backward we proved this formula, and after differentiation we get this formula dk equal to in terms of dE, that is root 2m by h cut square. Now we just substitute this dk here and we will get the gk dk, and from the formula we know that k is equal to this in the backward, and if we differentiate dk by dE, then we will get this expression. Okay, now if we now get the dk in terms of dE, now we can define this GEDE also. So when we write here dE, then this turns into GEDE. This will not be GKDK now, it will be GEDE. That equal to L by pi multiply dk. Dk is this, so dk will be this 2m by h cut square. Now this 2 came into this picture. Just what is this 2 which is defined? Otherwise it's just the same formula. In place of k we write E, GE, DE, and this dk we write this, and this is expression this. Now 2 is multiplied here. So why 2 is multiplied here? So GEDE is nothing but number of states, number of energy states. Now for single mode, now for the single mode or for single energy, we have two states of energy, means two states. For the single energy we have two modes. How? Because we are here, we are talking about the electrons, and electrons have plus half and minus half spin, and we can see that from the also Pauli exclusion principle says that two electrons can stay because of the opposite spin in the single state, in the single energy. So in the single energy we have two states. If we see this formula, the particle in a box, the energy given by this, and for the one, this is was the energy, and for the here one we'll get n pi x by L. And for if we talk about the wave function of this, then phi will be phi, psi will be phi 1 chi, and this. So the conclusion from here is this, you need to no need to understand this. Just it is that for each energy we have two electrons or the two states. Why? One from the plus spin and other for the minus spin, and that's how for each state we are getting two states. So that's why we multiply this, because we need to find the total number of states, and then we will divide it per unit energy, then we'll get the density of states. So if we multiply with 2, then we will get the total number of states, because at each energy we have two states. This is why we multiply here 2. Now the 2 will cancel out, and this will give us GED equal to L by pi root 2m by h cut square E minus half dE. Now density of states is nothing but number of states per unit energy. dE will come down and it will give us this formula. This is the energy density for a non-relativistic electron. Yeah, for the non-relativistic electron. Now in the question they asked us to plot this curve for the rho e and e. So it's for the e to the power minus half, so we can plot this like this, because from here we can see that when e tends to infinity, then rho e tends to 0, because it is negative, it will come down, infinity will divide and give us 0. So rho e will tends to 0 and e tends to infinity, and we e tends to 0, rho e tends to infinity. That will be the curve. This will be the curve. Okay. Now, if you understand these questions or how we find density of states, then try to solve these questions, some of these questions. In the next lecture, I will discuss these questions and move forward. But first, you should try to solve these questions, because these are not much hard, very easy. Find the density of states of relativistic field electron in 1D and also plot rho e versus E. We find the non-relativistic case. Now you need to find for the relativistic case. Just the same, you have to follow the procedure. And we know for the relativistic E equal to this, and it is given that ultra relativistic case means PC is very greater than m naught c square. So this will remain and this will dissolve, and it will give us energy equal to PC. Okay, this will overcome this, and E will be h cut kc, because P equal to h cut k, that will give us energy h cut kc. Now we've got this relation E and K. Now from here we can find the dk in terms dE in terms of dk, and just use this formula gk dk L by pi dk, and then solve. Just we solve the last question. Second question, you find the density of states of photon, then plot rho v versus v. Here mu is frequency. For photon we know that omega equal to ck, and omega equal to 2 pi nu ck. Here we get the relation between nu and k. Now just like we get a relation for E and K, and curve for the rho E, that's how you now differentiate with respect to dk, and you will get the relation between dk and d nu. Just replace here dk with d nu and solve the formula. You will get the answer, just same as we did before. Now there is the third question. Find the density of states of phonons in 1D and plot rho omega versus omega. Now for phonons we have this formula, omega equal to vsk. Here vs is velocity of phonon. Okay, you get the relation between omega and k, so you can find the dk in terms of omega, and just put in the place of dk d omega. With this relation, help of this relation, solve the likewise. The last question, find the density of states of manganese in 1D and plot. For the manganese we have this formula, omega equal to ak square, so you can find the dk in terms of omega, and you can use the formula we proved, gk dk equal to L by pi dk, and then you can plot rho omega versus omega. So try to solve these questions. In the next lecture we first briefly discuss these questions, the solutions, answers of these questions, then we'll go move forward in the 2-dimension, 3-dimension. Okay, so solve these questions and see the previous lecture if you didn't seen them. Okay, and you have to see these lectures more than one to understand this properly. So take care. Thank you.